This video examines mechanical switch noise, switch bounce, and its effects. We'll explore hardware debouncing solutions based on resistor-capacitor filter networks and dedicated logic ICs. These are some of the switches that we tested and looked at. Whole group of tactile switches we looked into. Here's a data sheet on a typical tactile switch. They quote their switch bounce at 5 milliseconds for the life of the switch, whatever that might be. In this case, 1 million operations, 3 million, 10 million operations. Through that lifetime, they should be the max is 5 milliseconds. What we found was most of the tactile switches were around 1.5 milliseconds. And here we have incrementing encoders, the data sheet here for those. And looks at what they're looking at as far as switch bounce. 2 milliseconds at turn rate of 15 revolutions per minute. Some of the test beds we'll be using to go through this testing and evaluation. R4 here, Smith trigger, RC network, IC solution. This particular IC is one of the only ones that you have to have a capacitor that you have to set the clock frequency, and that's that capacitor right there. IC solution here with the H7 Max series ICs, the L series. Switch bounce. Switch bounce is a mechanical action that occurs when contacts come together, causing a rapid making and breaking of action before the contacts come to rest. And that causes all kinds of problems, arcing, leading to degradation of contacts, metal transfer, and excessive static and neighboring electronic circuitry. Here's an example of switch bounce off a switch as we're looking at it with a scope. You see that the switch bounce, well, let's see, the time there is 200 on the horizontal, 200 microseconds. That's about 800 microseconds of bounce. Here's the basic RC circuit. You have a V plus voltage, charges through an R1 resistor, R2, charge the capacitor. On the discharge side, we have a discharge side through the discharge capacitor, or through the discharge resistor, back to ground. Here we have R4, and we're using a circuit here without Smith trigger, which is due to the fact that most of the microcontrollers have input hysteresis. They also have high, low levels, so it's possible to use these if you do the filtering correctly, so you don't have to use a Smith trigger. You can go directly into the chip. However, that won't work with most clock circuits or other circuits that may require that you use a Smith trigger. Here's an R4 threshold levels, high-low thresholds. They use VCC, which is over the supply voltage, normally 5 volts. So that'd be 8% or 80% of the applied voltage, 20% here of the 0.2. And also the R4 and the R3 had provisions for handling slow signals, slow rising and falling signals. They have a Smith trigger here in that input. Here you have some logic algorithms here, an edge detection circuit. On the SAMD21s, you also had a Smith trigger type of input before it goes into the synchronizer. So most of your Arduinos you can go directly into if you do the correct filtering. And here's another circuit, the RC circuit, the basic ones you'll see. A diode here. So on our charge cycle, we're going to bypass R2 and charge directly into the capacitor on the discharge, back through R2, through these closed contacts when they close to ground. We have a Smith trigger here at the end. This diode is, we'll show you later on in here that diode is not necessary. It's just, it makes the calculations, the charge, when we make our calculations for charge and discharge times. If we have this diode here, we don't have to, on our charge, we don't have to worry about this resistor here. So we can do them separately. We're going to set this circuit to charge-discharge time of 5 milliseconds. So what we're saying is it'll debounce anything that the bounce is less than 5 milliseconds. So we're going to set up this circuit for 5 milliseconds on the charge and discharge. And the following slides will show us how we did those calculations. And this is what we're trying to accomplish. We're trying to accomplish the switch bounce period to make sure that we set the timing on the charge to threshold so the switch bounce period is less than the discharge time to the threshold, in this case the low threshold. And that's what you'll have. You'll have a smoothing of the line. It's a kind of a slow fall here, falling edge, but the trigger from the Schmidt trigger triggers on that. Here we have the switch bounce period just a little bit more, or could be equal to. See, we didn't get the filtering. If this is true, the switch bounce period is less than the discharge time that we set by choosing the right resistors and capacitors. If we get this accomplished, you won't have this. You'll have this and you'll have that. Here are some switches that we chose. We tested. Input is yellow, the outputs are blue, and you can see the noise and stuff that they handled. And we got a clean, sharp, falling edge on the output. Here's the basic thing that we need to know about the timing and our calculations. We're going to try to set our threshold, the time to threshold on the charge side and the time to threshold on the discharge side to make it be longer than the time the bounce occurs. And we'll see that here on a few other slides, but these is about making all the calculations for that. And you can go back and read through some of this if when you get ready to make the calculations. These are the two calculations. Remember, we wanted to set both the charge, discharge, and the charge times for 5 milliseconds. So this minus t here will be the 5 milliseconds. So what we're doing, we want the switch bounce period to be, this is the time to switch bounce period, make sure it's less than the time that this thing, it happened before we discharged to the threshold, 1.6 volts. So the time for the discharge to 1.6, that time is greater than the switch bounce period. On this side, the charge time to our upper threshold, 2.5, we want to make it longer than the switch bounce period. And that's everything in a nutshell. And this talks about the calculations. Okay, we set the thresholds were based on the 7414. They usually use a 2.5 threshold on the high, 1.6 on the low. Little discharge diagram showing how the thresholds work. You can see as the threshold is low, it'll stay low until it goes above the high threshold, and it will not go low again until it goes past the low threshold. Here you see it went high, goes back down, and it's going to stay high until it drops back below the low threshold. And on that setting, remember we had the 5 milliseconds on the discharge, and we threshold. We wanted to make sure it was 5. So what this is saying, say it was 5 milliseconds based on this resistor, this resistance, and this capacitance. It'll take 5 milliseconds for that to discharge to 1.6 volts. And that's the calculations we made here. Okay, here's the calculation we made on the charge side. And again, what we're saying is to get to 2.5 based on a 9.63K resistor and a 0.68 microfarad capacitor, it'll take 5 milliseconds to get to 2.5 volts. And hopefully that'll be longer than the switch bounce period. And these are the calculations we made for both the discharge and the charge. So here we have the circuit. Now we're back to that circuit again. We've got our 5 on the charge and discharge. Discharge, charge. This one's a little less than the 5, but it's close enough. So you can go back through that slides, prior slides. It takes a little while to get a hang on what we're actually doing, but that's what the objective here is to get that timing so it's beyond the switch bounce. And we got back-to-back Schmidt triggers because we want the input, the input. If the input's high, we want the output to be high also. We don't want it inverted. If you just use one, it's high here, low here. And these are in the same package, so it's fairly easy. You put your input on 1, take your output off 4, and put a jumper between 2 and 3. Okay, another thing to be aware of when you do some of this stuff here, you want to keep your capacitor, your resistors, around about less than 40. This one's a little high, sometimes, especially for a discharge resistor. Press the switch. This will go low to ground. And you should have, normally if you have no leakage here, this should be ground potential 2 or 0 volts here. But because of the leakage on some of these ICs, especially the anything other than a 74HC, they have a very low leakage. And you see the leakage on these are very high, 20 or 40 times more. And what that'll do is this voltage will hang here at about 1.6, 1.5 volts, and it'll never go low. And we'll show you that on the demonstration. And just as a side note, most of all these circuits that we go through, there would be good options for most Arduino work with switch bounce around 5 milliseconds or less. Okay, some circuits here, different times. So you can see this one will, as long as the bounce isn't over 10 milliseconds, it'll do work for it, and as long as it's not over 19, it'll work. So these will work on most anything you have. Okay, here's something, this one's used on an encoder. They use this on an encoder sometimes. They have very low bounce, but you want the rebound to come back. You want it to charge back so you can twist it, because you're going to be twisting it. It's not, you're looking at both the falling and the rising and falling edges more so you get the little shorter time frame. These are all less than 1 millisecond. Okay, and here's an example of what you can do. You can get the same thing. You don't need this diode. We have the same timing on both circuits. This one with the diode, this one without. Although this one will require you to do a little bit more calculations, a little more math here, less here, because you're just dealing with this one. You're always dealing with just a resistor and a capacitor. Resistor-capacitor, this one you're dialing, you're going to have to integrate the charge with the discharge because you're charging through the discharge resistor. Recharge time 76 milliseconds, but that would work on most circuits because you're normally not going to be able to hit that button more than twice or more than one time before within a 76 millisecond time frame. Okay, here's a circuit here going directly into the R4. It worked on one switch. On the bottom switch, these micro switches are kind of noisy. It actually did a lot of ringing here probably because of this 5 volt. This is a pull down network. We're holding the input pin low and we're bringing it high on the switch actuation. So here we're going directly 5 volts directly into the capacitor, almost instantaneous charge, and that accounts for some of that ringing also. Here we clean that up. We put a resistor on that off that 5 volts, 6K, and that solved that issue. Now both switches will operate off this circuit. It did slow the curve down at the rise time, although the chip was able to handle it. And this one you can see the filtering was fairly good, and this is what we were talking about mainly. We delayed the time to threshold. So we slowed the threshold, we slowed the charge time down. So when it hit threshold, it was beyond the switch bounce, all this noise here. Okay, here's the calculations for that circuit. The first one with no resistor there. Very fast charge time, 20 nanoseconds. We slowed that down and got both of those switches to work. A little better operation. That's the timing on those. This one, 3 on the discharge, 2 on the charge. Very fast charge also. So we maintain this fast charge. That would be a good circuit also on an encoder. That's pretty good, right in that 3 and 2 range. Okay, we're working with a 3 volt system here, 3.3 volts on a H7 directly into the chip. We had good results with that. And the calculations, all the equations that we use that you'll need for doing this. And we'll look at these 3 IC solutions. The MC14490 is the only one that requires external component. You need that capacitor. It comes in, these are obsolete. You're only going to have to get these on eBay. These are available on most electronic DigiKey, Mouser, but they consider this dip package obsolete. But it'll handle 8 switches. It's got 6 debounce packages per package, 6 debouncers per package. So that was 8, but 6. Only 6, okay. TTL compatible, internal oscillator, voltage range 3 to 18 volts. So it'll work on a 3.3 volt system. And this is where your capacitor gas has to go between 7 and 8, 7 and 9 rather. Block diagram. And the only requirement here that they are stating out of all this, in order to obtain a bounce-free output signal, 4 clock periods do not occur while the input signal is in a false state. And we look at the timing here. This is the bounce. This is your bouncing here. We have to stretch the clock period out so it's longer than the bounce period. So that's what that is essentially saying. And the calculation for the capacitor for that is outlined here in this data sheet. But here's this kind of a spreadsheet we did, or cheat sheet, so to speak, that shows what we used, 1.1 nanofarad capacitor. That gave us the 2 milliseconds, and you can go down to the 5 milliseconds like the tactile switches. That'll handle most all tactile switches. You use a 2.2. And it'll probably work with the newer ones with the 1 nanofarad. But yeah, 1 nanofarad or 2 nanofarads will work. Okay, the Max series, 68, 16, 17, and 18. These are all surface mount. They don't make any dip packages, and that was the pricing at the time. Block diagram. You have 1 channel, 2 channels, and this one has 8 channels. So you could do 8 switches off this one, 2 off this one, 1 off this one. And they also come, if you want to work with the surface mount, they have these carriers that you can use and turn them into a dual inline package, a dip, so you can put them on your breadboard. And I think actually this company, this first company here, they'll mount them for you. Yeah, you specify the surface mount chip, and they'll mount the chip on a carrier. Okay, the LS10 series. Now these guys, they have both surface mount and dip packages. They have a 3-channel, 6-channel, and 9-channel. Now let's take an operational look at our RC filter network and Schmitt trigger. And see how it works. And first we're going to take a look at what happens if you don't have any switch debouncing. Put this filter here just so you can see the heart a little bit better. And we're going to give it 10 cycles. We should get a count of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see that's not the case. A lot of switch bounce there. So now let's switch this over. And we'll go through our RC network and Schmitt trigger. And see if we're hooked up on this side correctly into our Schmitt trigger output, generating an interrupt. And a count of 10 should give us a cycle of 10 should give us a count of 10. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's working. Now, because both your Uno R3 and R4, the inputs have a hysteresis built in with the threshold levels that are already built into the processor. So let's move this back over to before the input to the Schmitt trigger. Now we're just using essentially just the RC network without the Schmitt trigger. And theoretically, the processor should be able to handle that. Okay, we're reset. Let's try that count of 10 again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So your Arduino should be able to handle it even without the Schmitt trigger. Excellent. Here we'll demonstrate a debounced circuit without a Schmitt trigger on a 3.3 volt board, the H7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let's take a look at our bounce eliminator, our MC11 or MC14490 bounce eliminator. We have a capacitor used on this particular version. And we have a 1 nanofarad. It'll give us a 2 millisecond window. And if you want to go a little higher, you can go up to about 9 milliseconds with a 4.7 nanofarad. But here we're starting out with a 1 nanofarad. It'll give us a 2 millisecond switch bounce window. So we'll start off with our count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can reverse the count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On this side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can also go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And we'll count back 20. Now we're going back the other way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Back to 0. So eliminated the bounce. Good. Now we're looking at the maximum contact bounce eliminator. The max 6818. All 8 channels are filled up here. So we're going to take a look at that. We've got 7 plus 1 is the count reverse. So let's take it through a count up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll reverse. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And back to 0. Hold 1 down. There's a 1. Reverse count. Back 1, 2, 3, 4, 5, 6. 2 at a time. 7, 9, 11, 13, 14, because I hit the reset return button. Now we're going back the other way. Also toggles the light color as we toggle the count. Counting forward. Count backwards. Works perfect, and if you can look at this eliminator, the size of the eliminator, this is all surface mount. The Maxims, they all only come in surface mounts, but the surface mount chip that will debounce 8 switches is actually smaller than a single switch. Great. Now we're taking a look at the LS20 from Logiswitch. They make a 3, 6, and 9 channel bounce eliminator, switch bounce eliminator. And we're going to take a look at the switch first. There's a different range of switches we're looking at. And we're going to go bypass the eliminator and go directly to the switch just to see what the characteristics of the switch are, how much bounce it has. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I have 14 counts. Let's try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A lot of bounce there. Now we're going to go through the LS20 bounce eliminator, reset, try it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, eliminates the bounce. Let's try the other switches. In sequence, we'll reset, go 1, 2, 3, 4, 5, 6, 7, 8, and we'll reverse count. 7, 6, 5, 4, 3, 2, 1, back to 0. Reverse count. Reverse count. Reverse count. As advertised, eliminated the bounce. And that's the LS20 from Logiswitch. Here we have a working circuit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 40. And it's working circuit. And we're using a 74HC14. What you'll run into when you have a circuit like this, when you have a high value of R2, sometimes because of the leakage of the circuit, Schmitt trigger, it'll give you a problem and your circuit won't work. Right now this is a 74HC, and that's what I recommend you use. If we look at the input to the Schmitt trigger, it's at 4.9 volts. Hold the switch, it should go to ground. We're discharging the capacitor, and it should read 0. What will happen with a chip that has a high leakage current, it won't go low. It'll be stuck high, so your circuit won't work. And we'll demonstrate that here in a moment. I'm going to remove that HC and put an LS. And the same, it has a leakage of 20 microamps. 40 microamps is if you just use a 74 straight, 7414, that's 40 microamps. So that'll give you a problem again if you have a resistor of high value over about 40K at the input of your Schmitt trigger. So we'll demonstrate that. I'm going to take the 7414 out and put the 4 LS in, and we'll demonstrate that effect. Okay, now we have the 74 LS14 installed, so let's check that out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, it missed one. So let's see why. It's right at the margin. So let's look at the voltage and see what we have. 4.9 when it's high, and when I hit the button it should go low. Okay, well, 1.23 volts. It's not going low every time. It's right there at the margin. And if we do some chips rated at 20 microamps for the LS series 14, and we got 1.23 divided by that 43.2K, so that gives us 27 microamps. So that's what you'll run into. If this was a little lower resistance, it wouldn't be a problem, but it's biasing it high, so every once in a while it won't go low. So you have to be aware of that when you get anything other than a 74HC, which has only 1 microamp of leakage.